Okie dokie. So in this screencast, we begin a look at the derivative as a function, not at a particular value of x, but in general as a function. You will recall from our last lesson that we talked about the derivative at a point. We talked about what it was to take the derivative at a particular point like x equals a. We talked about f prime of a, and we found some derivative values at a variety of places, and the thought occurs to me, why would I want to find the derivative at 1, and then the derivative at 2, and then the derivative at 3? Aren't they all going to follow the same basic pattern? And the answer is yes. So we can talk about the derivative as a function where the slopes of the tangent lines are the values in our function. Here's the definition. The derivative of f of x, denoted f prime of x, represents the slope of f of x at any value of x. It is defined as the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. So this is the exact same, well, it's not the exact same, it is an analogous definition to the one we looked at last time. This is a general formula, whereas f prime of a will find things at a particular value of a. Couple of side notes. La, la. Sometimes instead of f prime of x, we use the notation dy dx. This is Leibniz's notation. He was one of the guys that developed the calculus. This should make us think about delta y over delta x without actually thinking about delta y over delta x. Sometimes we write the derivative with respect to x of a particular function. Instead of talking about f prime, we talk about the derivative of f with respect to x. So if we write this, we read it dy dx. We don't say over, we say dy dx. And sometimes in this notation, we would say the derivative with respect to x of f. So mechanically speaking, let's suppose that we want to differentiate, and that means to find the derivative of y equals x squared plus 2x minus 3. In other words, I want the slope of the tangent line at any point along that curve. So if I'm going to differentiate, if I'm going to find the derivative of, then dy dx is the limit as h approaches 0 of our function at x plus h. This is our function at x plus h minus our function at x. Well, this is our function at x all over h. And this is where algebra kicks in for us. Your denominator is pretty straightforward. Your numerator is a little bit of algebra. But you should notice that some things start canceling. Positive 2x, negative 2x, minus 3 plus 3, negative x squared, positive x squared. And you should notice that the remaining terms all have an h in them, which can be factored out and canceled. So we're going to factor out h from each of those, cancel it with that, and get 2x plus h plus 2. So now, let us actually take the limit as h approaches 0. As h gets closer and closer to 0, this gets closer and closer to 2x plus 0 plus 2. And so now I can know what the slope of the tangent line is at any value of x just by substituting that x value into here. If I want to know what the slope of the tangent line is at x equals 5, 2 times 5 plus 2 gets it done. Okay, a little bit more complicated. Let's find f prime of x if f of x is x divided by x plus 2. And let's do it using the definition. Using the definition, we've got the limit as h approaches 0 of our function at x plus h. This is our function at x plus h, minus our function at x over h. That's what we've got. So how do we proceed? Well, I'm looking for a common denominator for these two denominators. And the common denominator for those two denominators appears to be their product. So what happens? We get a really long fraction whose denominator gets left in factored form, and whose numerator, well, that's interesting. This fraction times this common denominator, the x plus h plus 2's cancel out, and you get x plus h times x plus 2. X plus h times x plus 2. And then this fraction times this common denominator, the x plus 2's are going to cancel out, and you get negative x times all of that. That's negative x squared, negative xh, negative 2x. And thankfully, stuff starts canceling right out. And then this h cancels with that one, and you get the limit as h approaches 0 of 2 over x plus 2, x plus h plus 2. Let us actually find that limit. What happens as h approaches 0? Well, the numerator is unaffected. The denominator is x plus 2 times x plus 0 plus 2. Well, that's just x plus 2 squared. So now, if I want the slope of the tangent line at x equals 0, I just substitute 0 for x. And if I want the slope of the tangent line at x equals 2, I just sub in 2 for x. So by doing the problem one time, by running the procedure through definition of derivative one time, I can find the slope of the tangent line anywhere I choose. One more thing in this particular screencast. There is an alternate definition of the derivative. The alternate definition of the derivative says that if I want f prime of x, I take a limit as z gets closer and closer to x of f of z minus f of x over z minus x. And all that does is it establishes that there are 2 points on the curve. One is the point we're interested in, and the other is some generic point nearby. And then this is just a standard slope. It's change in y over change in x. So if my function is the square root of x, and I'm interested in the derivative, well, I could take the limit as z approaches x of f of z minus f of x over z minus x. And then you know as well as I do that since it's got a radical in a binomial, the way out of that trouble is to use the conjugate. And when we use the conjugate, these drop, and you're left with z minus x, which conveniently cancels out with that. Let's let z get closer and closer to x. As z gets closer and closer to x, these two things become the same. Got it. That is the other way to get a derivative from a definition. Okay, so in the next video, I'm going to talk about how you can sketch a graph of a derivative based on a graph of a function, and we're going to talk about situations where a derivative does not exist. So if you are already comfortable with that, then awesome, and if you are not already comfortable with that, then you should be. Thanks.